So hopefully that seems to solve the problem. It was redlining for me, and I'm not entirely sure why it was doing that. Redlining meaning there is. I mean, I can show you what OBS looks like. There's like a little bar here that tells you, how you're doing. There's this drop frame percentage, and that was like hovering around 50, and this bar was red. Apparently, it was good for your end, so I'm not sure why that occurred. I just wanted you to know that's what I was seeing. Anyway, to that end, so we want to go through a tree just like a list or a set where we visit every element at a time. And we know that we can do this because we've done it before with a tree set. So if I just create let me close this. If I just create a quick little test file, tree set example, and then I do public static void main string args, and I just create a simple tree set string words equal new tree set string. Import that. Then from there, words dot add there. Well, let me make it all lowercase. There. Once was a man. Something like that. From there, if I were to say for string s in words, system.out.println s, you'll see that it prints the words in alphabetical order one at a time. And as we talked about, this tree set is a binary search tree. And so, because of this, we know that there is a way to iterate through a binary search tree, because if Java did it, we can do it too. We're not... Java's built-in code is not special. It doesn't harbor any dark arts. So how do we step through a tree, like a binary search tree, in order, for example? And to that matter, how do we step through any tree? So, going back, if this were our tree, any of these, how would we step through it? Well, all of these approaches really could work. For example, this, as we'll talk about later, is an example of a depth-first search. This is an example of a breadth-first search. And this is an in-order traversal. And we'll talk about what all those mean here in a second. But the idea of a traversal is it a particular way to step through a tree, visiting one node exactly once, such that every node is seen exactly one time. So for example, we wanted to print, we would traverse through and print every value. And for a binary tree, notice it doesn't say binary search tree, just says binary tree. There's three basic traversals: pre-order, in-order, and post-order. And this order is applied recursively. So this function can be defined recursively. And so, in each technique, the left subtree is always searched before the right subtree. Forgive me. Pardon me. Sorry. So we always go down the left before we go down the right, regardless the order. Thank you. Rather, what distinguishes the tasks is the order of these three tasks. That is, we go down the left, the right, and we also visit the root. And which order it goes in defines pre-order, in-order, and post-order. So, in a pre-order traversal, we visit the root first, then we traverse the left, then we traverse the right. In post-order, we go left, right, and then root, and then in order it goes between. And so, setting up my whiteboard camera here. And so you can think of this. Sorry, I knocked that over. Well, my chair did anyway. So you can think of this simply as you're always going to have left and right in that order. Always going to be left before the right. From there, in pre-order traversal, you visit the root first. So it goes root, left, right. In post-order traversal, it goes left, right, root. And finally, in order traversal, we go root in between. So left, root, right. So the left, right's always there. The pre tells you it's before the left, right. The post tells you it's after the left, right. The in tells you it's in between the left, right. That's the mnemonic device to think of. And it turns out that these are actually fairly simple to code. So for example, let's say, going back to the example that I had yesterday, if we have this binary tree, let me go to the binary tree we worked on yesterday. Oh, I don't have that anymore. That was a mistake. If we go to our binary tree node, like we had yesterday, the idea is, and in this case, it is a binary search tree. You know, the idea was we created all these nodes. Let's go ahead, and I'm just going to create a few more. So the root is 6, left is 4, left is 3. Let's go ahead and do root left dot right is 5. Root left, or root right is going to be, let's do 8. Root right dot left is 7. And root left dot left is going to be 10. If I were to print this tree, it prints in a particular way. And this particular way of printing is, oh, sorry, I made that left instead of right. Sorry, that was a mistake. And this particular way of printing is actually demonstrating a post-order traversal. So here's what I mean by this. Let's draw this tree that I have. I have 6 as the root, then on the left it's 4, and then 3, 5, and on the right it's 8, and 7, 10. So I can draw this tree on the whiteboard to use as a working example. So I'm going to start with my root of 6, and this is a binary search tree, but remember that these traversals can be used on any binary tree, not just a binary search tree. 4, 5, 3, and on the right I have 8, 7, and 10. So here's what I mean, for example, with a pre-order traversal. I'm going to use pre-order in blue. The idea of a pre-order is I start at the root, like all traversals, and the first thing I do is I visit the root. So I'm going to just say, let's say when we visit, we print. You can do other things when you visit, but let's for now say we're just printing. So pre-order is going to be 6, and then I go down the left, and I visit 4, and then I go down the left, and I visit 3. 3 does not have a left nor a right, so I recurse back upwards. And then I need to visit 5, the right side. 5 has no children, I go back up. 4, I've used both children, so I go back up. Then I go down the right side, I visit 8. Then the left side, I'm going to visit 7. 7 has no children, recurse back up, go down the right side, I visit 10. 10 has no children, recurse back up. 8 has no more children, recurse back up. 6 has no more children, and we're done. This would be a pre-order traversal. Now, let's try doing a post-order traversal. And let's see what that looks like, a post-order traversal. A post-order traversal, which I'm going to do in green, we visit the node at the root after we use both children. So, we start at 6, but before we visit 6, we go down the left. And then before we visit 4, we go down the left. And then we go to 3. 3 has no left child, it has no right child, so now that we've used both children, we visit 3. Then from there, we come back up. 4 still has a right child, we go down the right. 5 has no children, so then we visit 5. 5 then recurses back to 4. 4 has no more children, so we visit 4. Recurse back up to 6. 6 still has a right side. And that leads us to 8, but 8 has a left child, 7. 7 has no children, so we visit 7. Recurse back up to 8. We then go down the left side, or the right side, excuse me. We visit 10. 10 has no children, so that's why we go immediately to 10. We recurse back up to 8. 8 has no more children. Recurse back up to 6. And there we go. And the important kind of dead giveaway here is with a pre-order traversal, the root will always be first. And with a post-order traversal, the root will always be last. Given this demonstration, I want you to try, and you can jump into Discord, help each other out with this, see if you can by yourself do an in-order traversal. Remember that in order is left, then self, then right. Or left root right. Try and write out what an in-order traversal looks like on this binary search tree. Take a minute and work on this with each other. And if you think you have it, feel free to write it into Twitch chat. If you think you have it. Remember, you go left, then yourself, then right. You don't go left, right, and then self. Oh, wait, I may... no, this is... Yeah, I did this right. Remember that you do it at every level, not just the root. At every node, you go left, then self, then right. I'll give you a hint. There's a reason it's called in order. Let's go ahead and give this a shot. Alright. So now, where'd my red marker go? It fell on the floor. There it is. All right. So we start at the root, but before we visit 6, we have to go down the left side. Before we visit 4, we have to go down the left side. So we visit 3. 3 has no left child, so we say 3. Now, 3 has no right child, so we recurse back up to 4. 4, we've now visited the left, so we visit itself. We visit the root, 4. Then from there, we go down the right side. 5 has no left child, so we visit 5. 5 has no right child. We recurse back up. Now we come back up to 6, and because we're done with the left side, we now go ahead and visit 6. We then recurse down the right. We visit 8, but before we do anything, before we actually visit 8, we're going to go down the left again. Now we're at 7. 7 has no left child, so we visit 7. 7 has no right child. We recurse back up. Now we're done with the left side of 8, so we visit 8. Then we go down the right side. We're at 10. 10 has no left child, so we visit 10. Then we recurse back up, and we're done. Hey, wait a minute. Does this look interesting to anyone? Anyone recognize any pattern here? What is this? What's unique about these numbers? They're in order, or they are sorted. An in-order traversal of a binary search tree, not a binary tree, just binary search trees, will always be sorted. It doesn't matter what the shape of the binary search tree is. If it is a valid binary search tree, the in-order traversal will always produce a sorted list of numbers. Pre and post will not do this. Are there any questions about the in-order traversal or any of these? Any questions about any of these? So given this, let's take a look now at the toString function for the code for the daily activity I gave you yesterday. Notice that the toString function says the string return value. It does the left return value plus, or this dot left toString. Then it does, if the right is not null, return value plus this dot right dot toString. Then it does return value this data. Then it returns. What traversal is this? Is it pre, post, or in? Write in Twitch chat which you think it is. Pre, post, or in. Remember where we visit the given node, because this is in the binary tree node. So we would start with the root and recurse left and right and then get the value. Is this pre, post, or in? I think we are seeing one of the great cognitive biases on play here. One of the cognitive distortions, which is called the anchoring effect. This is not pre-order. Here's the thing. Remember the order. That's true too. That's also true. But when do we visit the left? First. When do we visit the right? Second. When do we visit this? Third. This is post order. And if I were to run this 3, 5, 4, 7, 10, 8, 6, you'll notice that it matches on the whiteboard 3, 5, 4, 7, 10, 8, 6 my post order 3, 5, 4, 7, 10, 8, 6. So this traversal, this is right now a post order because of where I am recursing. Where I'm recursing left first, then right first, and only then do I visit the data. I can easily make this a pre-order traversal. Here's how I would do this. Control X, Control V. Now, I visit this data before I go left and right. Because remember, these lines of code are executed in order. And so, this will produce, printing the tree, 64358 Taking a look at the whiteboard, what was my pre-order? 64358 So, pre-order, it goes here. Post order, it goes here, and therefore in order, I simply drop it right in the middle here. 3, 4, 5, 6, 7, 8, 10. That's all there is to it. It's where this visiting this data goes. Are there any questions about this? Is there ever right root left? No. We always, in a binary tree traversal, we always go left first. It's just how we do it. I mean, okay, could you write a traversal that goes right root left, or right left root, or root right left? Yeah, you could absolutely write that if you wanted to. But we don't have a special name for it because it's not particularly common. It doesn't technically, because you could just, I mean, all that would do if you went root right, right root left, it would just do descending order. If you did root left right, or sorry, root right left, I think it would just be the opposite of an in order traversal. I think it would just be in reverse order, although I'm not certain of that. And then if you did right left root, it would just be the opposite of a post order. I mean, so you can do that. Like, yes, there's no cosmic force stopping me from doing that. Like, nobody's gonna die just because I moved this here. But we just don't have a special name for it because we don't really do it. It's just not a common thing to do. Could you? Yeah, sure. Might there some day and time be a reason to do that? Maybe. But we just don't. It's just not a common thing to do. The ones that we care about all go left right. So root left right, pre. Left root right, in. Left right root, post. Which is all captured pretty handily on this slide. The question is, can you? Absolutely. Is there a reason to? I've not run into one. But that doesn't mean there would never be a reason to. I haven't run into it. Alright. So again, you can see, given this tree, here's the example. I encourage you, on your own, I encourage you to just not look at that and only do pre, post, and in order here as practice, and then check your answer against the slide. Now, a pre-order traversal also serves as a simple form of a depth-first search. We'll talk about that later. The pre-order traversal is also used for something called prefix notation. Prefix notation is a... by the way, we won't revisit this later because we don't cover grammar in this class anymore. But there are some languages that use prefix notation. So there's a language called Lisp, and Lisp, there's no operators. There are no operators at all. There are only functions. And so if you were to write something in Lisp as a mathematical formula, you would maybe say something like, let's say I wanted to get the positive root of the quadratic formula. That is, there's generally the positive and the negative root. The way you would do that is instead of saying negative b, you would say minus 0b. The function is subtraction. The first operator is 0. The second operator is b. From there, since this is the positive root, we're doing plus, and we're adding that to, because remember, this is a function. This is the first argument. The second argument is itself a function, square root of, and you can kind of fill in from here. It would be plus and, something like that. If I wanted to write, let's say 5 minus x divided by x minus 2. Let's say I wanted to solve this. The function between these two is divide by. The numerator is minus 5x. The denominator is minus x2. Now, I am not expecting you to look at this and be like, oh, that makes sense. I just want you to know that this is a notation that exists, that there are languages that use it. And it's because we don't have operators, these are all functions. And if you write your grammar this way, actually early grammars were often written this way because it was quite easy. It was quite easier to do. You treat every operand as a function and everything as arguments. It makes your syntax a bit simpler. So this does have a use. This pre-order traversal is often used to make syntax trees. What is that? It's like a stack. Yeah, exactly. It uses the stack heavily. The idea of a stack heavily. In order traversal, pretty standard use case is just to visit elements from smallest to largest if it's a binary search tree. Again, only for binary search tree, not for a binary tree in general, because a binary tree in general doesn't necessarily have order. In order traversal, you would build an expression tree. Pretty much, this would be how you would write it as a human being, how you would write an expression, and so that's useful for in order. There's also postfix, which is just the opposite of prefix. Although it uses actually a queue, which is a bit harder. But yeah. So from there, let's start with practice. I want everyone, and hop in Discord with each other. I want you to try to do first the in-order traversal of this, then the pre-order, then the post-order. So one last little quick exercise before we move on. Don't write it in chat yet. Just write it down on a notepad file or something. But you can jump into Discord and work with each other on this. Right now, it looks like there's only 3 people in Discord. I want to see more hop in, work with each other. Because remember, even if you think this is easy, someone else might not, and you're helping them. So take a minute. I will give 2 minutes on this, and then we will go through and just rapid fire through the answers in order, pre-order, and post-order. All right. All right. Who wants to give a shot to in order? Anyone? Who wants to give a shot to in order? We'll start with that one because that's arguably the easiest because all you're doing is just alphabetizing things. Because this is sorted. This is a binary search tree with the strings sorted in alphabetical order. So, remember, we would go down the left side. So we go Luke, then Han, then Chewbacca. Chewbacca has no left child, so we visit Chewbacca first. Has no right child, we go back up to Han. We now visit Han, so we're at Chewbacca Han. Han then goes down the right side to Leia, but Leia has a left child, so we don't visit Leia left. We go to Lando. So we've done Chewbacca, Han, and now Lando, because he has no left child. Then Lando has no right child. We recurse back up to Leia. So now it's Chewbacca, Han, Lando, Leia. There's no right side. We go back up. Now we visit Luke. Chewbacca, Han, Lando, Leia, Luke. Go to Vader. Vader has a left child. Obi, so Obi-Wan. So then Vader, then Yoda. And if you look, Chewbacca, Han, Lando, Leia, Luke, Obi, Vader, Yoda. You can, of course, take a look at these slides to see if you didn't get that solution. Just get some more practice with it. As well as pre-order. You can see the solution here. Remember the dead giveaway that Luke is the root, so it's always going to be first. And in post-order, Luke is the root, it's last. Now, that does not mean pre- and post-order are flipped, because they're not. They're not opposite. You know, Chewbacca is the third element, it's the first element here. So, just keep that in mind. So where would we do traversals? I mean, printing a list is one. You can use it as a way to determine the tree height. You can use it to determine the tree size, the number of nodes. You can use it to make a deep copy, etc. To that end, now, in addition to traversals, we want to talk about searching. And there are two broad means of searching. There is a breadth-first search, and there is a depth-first search. And they are different. So depth-first search is a bit easier. The idea of a depth-first search is that we're going to start by pushing some root value onto the stack. Then while the stack is not empty, we pop one value off. We find all the children. That is, we process this value. We check if this is what we want or whatever. But then for each child, we push it onto the stack. And this is often used in things like chess, although you wouldn't do a complete depth-first search. You'd see it modified. Of course, now modern chess algorithms don't actually do this. They use neural network models. But let's do an example. So let's say I had this tree. So let's actually draw this graph onto the whiteboard. And ignore the edge numbers for now. We're not interested in that. That would be used in Dijkstra's algorithm. We're certainly not getting into that in this class. So the idea is I have A, which for now, I'll call my root. A points to B. A points to D. B points to E, which also A points to. There's also a C up here that points this way. And again, this is very much not a tree, what I have here. This is very, very, very much not a tree. And from there, I can visit each of these nodes with a depth-first search in the following way. So initially, I'm going to have my stack. And I'm also going to keep track of a list of processed, or a set of processed nodes. And initially, both of these are empty. And I'm going to push onto my stack, initially A. Now, what do I do to follow this depth-first search algorithm? What we do is while the stack is not empty, we're going to pop A. So now we're looking at node A. We process A. And now we're here and we need to push onto the stack all of A's children. Now the order here can be somewhat arbitrary. You could do left-right, but in this case, not a binary tree. We can't do left-right. So let's just say I push alphabetical order. I'm going to push B, then D, then E. I could also push in reverse order, so if it says starting with the last one, I could go E, then D, then B as well. E, D, B. Now, I pop B off the stack, I process B, and then I push all of B's nodes onto the stack. So I'm going to push E, and you may notice E is here twice. Don't worry about that for now, because I'm going to throw a wrinkle in this later. Now I pop E off the stack. So I'm at node... I've visited B, now I'm at node E. E's only child is F. So I first process E, and then I push its children onto the stack. So I want to show the path I have traced so far. Then from there, I pop F. I process F. F has one child C, which I push on to the stack. Then I'm done with that. I pop off the stack C. I visited C specifically from F. I process C. And then I push all of C's children on the stack E. Except what I can do to avoid getting stuck in an infinite loop here is I can say, oh, well, I've already processed E. It's in this set, so I'm actually not going to push E onto the stack. I'm going to skip it. Then from there, I visit D, which I did from A, but keep in mind that that means now I'm going to D from A. And I'm just going to do this a bit more quickly now. I process D. I push its children onto the stack. G in reverse order, so H and then G. And so on. This could be how you do a depth first search on a graph. On a tree, it's a lot simpler because you don't have to worry about cycles. Because in a tree, we never have cycles. And so, if I were to do a depth first search on a binary tree, and I'm explicitly not saying a binary search tree here. So a binary tree, go 5, 7, 3, 1, 8, 4, 10. And actually what I'm going to do is I'm going to remove this one and I'm going to put it over here. And let's say I were searching for the value 1. I start with the root. Here's my stack. I start with 5. I pop 5 off the stack. Let's say I were looking for 1. This is find 1. Well, in this case, 5 is not 1. So when I process it, that's false. So I check the left and right. So I'm going to push in reverse order. So right, then left. 8, 7. I pop 7 off the stack. 7 is not 1. So I push its children onto the stack. 3. So at this point, I have gone down this path. 3 has, I popped 3 off the stack. It's not 1. It has no children. At that point, there are no more values to push onto the stack. 3 has no children. So now I go to 8. So just to number the order. 1, 2, 3. With 8, I pop it off the stack. It's not 1, so I push its children in reverse order. 10, and then 4. Now I pop 4 off. Pop 4 off the stack. 4 is not 1. I'm going to push its children on 1. And then I pop 1 off the stack. And 1 is the value I'm looking for. And so at that point I can return true. This would be a depth first search. And the way you can think of this is, we had a graphic for this just a second ago, is like the graphic here on the right. You can see we go down the left side as far as we can. When we can't go any further, we go back up and then traverse down the right side. This, if you'll notice, is a pre-order traversal. So a pre-order traversal is just a simple depth first search. And remember, this works on a binary tree, not just on a binary search tree. And technically this would work on any tree, not just binary trees even. A breadth first search, it's a little bit different because the idea is rather than going as far as we can and then traversing back, we actually go one row at a time, visiting every node along the way. And the way we do that is instead of using a stack, we use a queue. And that's the only difference. So if I did a breadth first search, over here, rather than using a stack, we simply use a queue. And it works the same way at that point. But think of my queue as like a line like this. Here's the front, here's the back. So I start by in-queuing the root. I dequeue off the queue 5. 5 is not 1. Again, the idea is I'm looking for 1. And so I'm going to look and in-queue the left first, and then the right. So I've in-queued the left and the right. Then I dequeue 7. So I have gone down this path. That's my first move. I dequeue 7. 7 is not 1, so I in-queue its children 3. In this case, it only has 1 child. Now, before I visit 3, I actually stop and I go and I visit 8 because I dequeue decide the next value I'm going to look at. And 8 is at the front of the queue. I then in-queue 8 children, 4 and 10. And then from there, you can actually follow. I would go, this would be my 3rd move. This would be my 4th move. And then I would in-queue 1, but that 1 would go back here behind 10. At that point, 4 would be dequeued. Then 5, and then 6. So in this case, it took more moves, although sometimes a breadth first search can be better than a depth first search. If your value is likely near the root of the tree and the tree is very tall, a breadth first search will be better. But you can think of this as though we're just going left to right, one level at a time. That's the idea. So the difference between a depth first search and a breadth first search is effectively just what data structure you use. If the data structure is a stack, we're talking a depth first search, and if it's a queue, it's a breadth first search. In practice, I will say that a breadth first search will typically require a lot more memory than a depth first search. So that is something to keep in mind. Give me 1 second. All right. Any questions? Okay. So from there, now that is our unit on traversals. We're done with that. The next thing we're going to talk about are heaps. But before we jump on to talking about heaps, There was an in-class activity, but I decided to do the in-class activity on Heaps instead. Before we go on to talking about Heaps, we're going to take our usual break. We're going to take it a bit early. So we'll be back here at 2:57. So let me put that message up. Not 2:57, excuse me, 2:07. We're not taking an hour-long break. Sorry. But we will be right back. We'll come back. We'll talk about Heaps. I did mean 2:07. We'll come back. We'll talk about Heaps. And then if we finish early today, we finish early today. And we very well might. So I'll see everyone then. Be right back. All right. Sorry, I'm a little bit late getting back. Just had an email that I needed to respond to. But with that, now let's pick up and let's talk about binary heaps. So a binary heap is a type of binary tree. It is a special version. Hang on, I need to delete this. So a heap data structure is explicitly a balanced binary tree, and it adheres to a particular set of rules that we will discuss. Namely, though, the heap is useful for finding the largest or smallest value in a set. It is also useful for sorting in ascending or descending order. There is such a sort as a heap sort. And it's also useful and often used for implementing something called a priority queue. Now, I'm not going to worry you too much about how the heap, as we've talked about the stack and the heap, how the heap is actually organized. Rather, in this case, don't get too caught up in that and just think of this kind of heap as separate from the other kind for the time being. So this heap is a binary tree that adheres to a specific set of properties. The first property is the shape property. It is a complete tree. That means that every layer above the bottom layer is completely filled with no gaps, and that all the nodes on the bottom layer are as far to the left as possible. And the second is the order property. So if, for example, we were talking about a min heap, that is a minimum heap, then every parent is less than all of its children. In this case, because there's a binary tree, both of its children. So the parent is less than both child, left and right. The heap does not distinguish left and right. Where a binary search tree, left and right have a meaningful distinction, in a heap, we don't distinguish left and right. We just think of the relationship as parent and child. We don't think about left and right uniquely. So, for example, this is a heap that adheres to both the shape property and the heap property. And this is specifically a min heap. So I'll zoom in on that a bit. And actually, while I'm at it, let me turn off the be right back message. So this heap adheres to the shape property. The top 3 rows are all complete, right? There's no gaps. And the bottom row, every node is to the left side. Further, the heap property is adhered to where for every node, its children are of greater than or equal value. So 25 is greater than 15, 16 is greater than 15. 17 and 18 are greater than 16. 78 is greater than 25. 80 and 90 are greater than 78. Now you may be thinking, but wait a minute, 42 is less than 78. How is therefore 42 a layer below 78? Well, that's because with a heap, again, we don't care about left and right. All it means is that every descendant of 78 must be greater than or equal to 78. Siblings have no relationship here. So, and given so far we're defining a min heap, we could just as easily flip that to be a max heap. We would just flip the heap relationship. So while I'm talking about a min heap today in class primarily, just understand that trivially we could create a max heap with the same rules, just flipping the parent-child relationship. So again, this is a valid min heap. A heap is not a binary search tree. The left can be larger than the right can be larger than the left. There's no distinction. All it means is that the parent is less than the child. So given that, the following, which of these binary trees are heap? A is not a heap because A is not complete. If I move 51 and 56 to be children of 30, it would be. But you can see here there's gaps in the not bottom row. The bottom row, yes, the values are all to the left, but the next row up is not complete. 30 has 2 null children. B is not a binary heap because it doesn't adhere to the shape property. If I moved, say, 51 over to be a child of 20, then it would be. But for now, this is not, because it's not complete, and the children are not all the way to the left on the bottom row. This, over here on the right, is a complete binary tree that adheres to the shape property. And so this is, of the 3, the only valid binary heap. So again, just keep that in mind. Any questions about the shape property or the order property? So again, here's another example. Here you can see we have a missing space. A complete tree is not necessarily a heap. A heap is a complete tree, but the shape property is not the only property. So when we're talking complete, that is only sufficient for the shape property. So being a complete tree is necessary to be a heap, but it is not sufficient. We have to adhere to both the shape and the order property. Both of these conditions have to be met for this to be a heap. If one of these conditions fails, it is not a heap. And we'll talk about why the shape property and the order property are in play a bit later. Yeah. So think of, again, the shape property. It must be a complete tree. Nodes are added at the lowest level from left to right, and nodes are removed from the lowest level from right to left. That's how we adhere to this. So, where are nodes added and removed? This is a bit interesting. We remove nodes, in theory, from right to left on the bottom, and we would add a node as a child of 12. Now, we wouldn't remove the value 90. I want to be clear about this. We'll talk later about what value we remove, but if we were to delete a node from the tree, it would be this node. And if we were to add a value, it would go in this box here. So how do we do this? Well, there's really only 2 methods. Does the heap always have to have the order property? Yes. The heap, you have to enforce the order property. The heap will not do it automatically. So when we insert and remove values, we have to apply the order property. We're going to have to enforce that, and we'll look at examples of how we do that later. So we really only care about 2 options with a heap. Inserting a new value and retrieving the smallest value. Now you may be thinking, wait, I just said I'm going to remove a node. I'm removing the node, but I'm not removing the value 90. If I were to remove a value from this heap, the value removed would be 15. That would be the value I would remove. And so, to this end, the way that we think of heaps in this case is we think of heaps as a useful way to remove, in the case of a min heap, the minimum repeatedly, or in the case of a max heap, the maximum repeatedly. Sorry, I had a bit of cat fuzz on my head. My head does feel weirdly itchy. I don't really have a good reason for that. Anyway, from there, let's actually illustrate how these are done. So if I were to add to a heap, let's say I add the value 35, I would simply add it again to the first available space, which is the left child of 35. And at this point, the heap property is satisfied as well as the shape property. So this is a valid heap. So I'm done. If I added the value 35, easy peasy, I'm done. But now let's add the value 9. Now with 9, we have a problem because 9 is not less than 17. Therefore, if we add 9 here, we violate the heap order property. So what do we do to fix this? Well, we just swap 9 and 17. We can just swap 9 and 17, so 17 will move down here, and 9 will move up here. So we end up with this. But this still does not satisfy the heap order property, so we swap 9 with 16, because 9 is less than 16. And then we swap 9 with 15, because 9 is less than 15, and we end up in this. So because we added 9, we had to swap a bunch of values. Given that this is a heap, it is a complete tree, what is the runtime, therefore, in the worst case of insert? In the best case, it's constant time. What is the worst case runtime? It's log n. It's O log of n. Because the height of the tree, because it's complete, is log base 2 of n. It cannot be larger. The nice thing about this is, when I talk about binary search trees and I say, well, the runtime is log n, and then I have to quickly add, before anyone notices, assuming the tree is balanced. With a min heap, we don't have to make that assumption. The shape property ensures that it is balanced. And so all we do when we add is we add the node, and then if we need to swap, which we don't always need to, if we need to swap, we continue swapping until we are satisfied. And that doesn't mean that we're always going to swap all the way to the root. In this case, we did. But if I were to take a heap, if I were to take make my own heap here, let's do 15, 16, 25, 30, and let's do, let's say I'm adding a new value 20. So I add the new value 20, which I'm going to use red to denote that. But now this heap order is violated, or the heap order property is violated. So I have to swap 20 and 25. So I just swap the values in these nodes. I don't delete the nodes. I don't remove anything. I just change the values in them. 25. And then 20 is greater than 15, so I'm done. So in this case, I did even less than log n steps. So in a worst case, this is O log base 2 of n. In a best case, this is O of n. In an average case, it's going to be half of log base 2 of n. But as we talked about before, if you multiply this by the constant 1/2, it's still, sorry, in the best case, it's O of 1. It's still log base 2 of n. There we go. Now, that's how we insert values. So let's insert another value. Let's say I were to insert 17. If I insert 17, hey, I'm done. I don't need to do anything else. If I insert now 15, because you can have duplicate values in a heap, there's no rule against duplicate values in a heap. If I insert 15, I have to swap 15 and 16. But then from there, I don't need to swap 15 and 15 because they're equal. If I swap them, nothing would happen, so I can stop there. Now, we're not getting into the mechanics of how this is done yet. And I will talk about how this is done, how this heap is implemented. But we're just focusing on the high-level operations. Are there any questions about inserting into a min heap? And again, if this were a max heap, I would just change, instead of the root needing to be the smallest value, the root would be the largest value. And you could restructure this to be a max heap, but for now, we would never switch between the two. Something's either a min heap or a max heap. So for now, inserting into a min heap. Any questions? All right. So now we need to delete. So when we delete a value, we always remove first the value from the root. Because the idea is when I remove something from my heap, specifically the value I want to remove is the smallest value. And so, the key is, however, I'm not removing the root node. It removes the value at the root, but not the root node. Here's what I mean by this. If I were to remove from this heap, the first thing I would do is I would copy this value 90 and I would save the value 15 to be returned later, but then I would overwrite this 15 with 90, and then I would delete that node. And I need to store 15 to return later. We've done that before with the queue. So you can go back and look at that. You just create a variable. Simple enough. From there, though, now you'll notice that this heap is not valid. So let's take a look at how we fix that problem. So, the first thing we do is we swap 90 up to the root and then delete that node. Then, 90 is greater than both 25 and 16. And we need to swap 90 with one of these two. Now, if we were to swap 90 with 16, you can see that now 16 is less than 25 and 90. This is fine. If instead we were to swap 90 with 25, this would not work. This would be 90, and this would be 25. And you can see that right now this is not a heap either, because 25 is less than 16, so this is not adhering to the min heap. So we have to specifically swap the value with the larger child. So because 90 is greater than both 25 and 16, we swap 90 with the larger child. Or excuse me, we swap 90, with the smaller child. So we swap 90 and 16. Then from there, 90, 17, and 18, we swap 90 with 17 because it's smaller. And now this is our new heap. Now we return the value 15. That was the root. But this is how our heap changes. And this is how we preserve the shape property. In a worst case, given how I illustrated this, what is the worst case runtime of remove? What's the most number of values you would need to possibly swap with? Once again, it's log n. So that's pretty good. Log n's pretty good. So let's go back to the whiteboard, and let's do a couple removes here so you can see how it's done. Let's do a couple removes. So first, if I'm going to remove from this heap, I'm going to first store this 15 in a return variable, just some int containing 15, and I'll return this later. I then take the value in the last child, the farthest right child on the bottom level, I copy it here, and I delete this node. And now I simply need to fix the heap. 16 is not less than 20, but it is, or 16, is not greater than 20, but 16 is greater than 15. So I have to swap these two. So I swap 15 and 16, but now 16 is less than 17, so I'm done swapping. I don't need to do any more swapping. Let's remove again. I remove the value 15. I copy this value 17 up to here, and I remove this node. Now I need to fix 17 less than 20, but greater than 16. So I swap 17 and 16. And then I return 15. Let's remove again. I store 16 in my return value. I swap 25 with 17. I delete that node. And then 25 is greater than both 20 and 17. That means I swap with the smaller child. So I swap 17 and 25. And then I return 16. So that is removing. Any questions about remove on a heap? Any questions about remove? Does it, let's see. So again, because of this, why keep a balanced tree? It makes sure that everything is log, adding and removing elements in a worst case is log base 2 of n. Now I'm going to blow your mind, because these heaps are not implemented like we've implemented binary trees. We can implement these heaps with arrays. For example, let's implement this heap that I have here as an array. So first, let's draw it onto the whiteboard. Because it turns out that it's actually more efficient if we do this with arrays than with linked data structures. And because of the shape property, we can do that. I don't know why I'm out of focus. Let me... There you go. That seems to have fixed it. Okay. So, 16, 25, 17, 40, 78, 90, 18, 50, 42, and 80. Now you may think, okay, well these look like nodes with left and right child. So how is this not implemented as a tree? Well, this is how we visualize the heap. But we can implement the heap, and technically we can implement binary search trees the same way, but we implement the heap as an array. Specifically, the completed tree would have, it would be 4 layers down, so it would be 1, 3, 7, 15. So it would have 15 slots. That means I'm going to create an array of size 16, and there's a reason I'm creating it of size 16. I'll feed you. Me get there first. That's 8. That's 16. Now there are 2 ways to do the heap. So I'm gonna write them a bit differently. And again, this heap can also grow if necessary. But there's 2 ways to do the heap. The first I'm going to do is a 1-indexed heap. And it'll make sense why I'm allowing for a 1-indexed heap. And the second is a 0-indexed. In a 1-indexed heap, we ignore index 0. This is index 0, but we're just not going to use it. Instead, we fill the values in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Whereas in a 0 index, we would use the 0 value. And the order that we're going to fill these values in is the order of a breadth first search. So this will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's no node here, but this would be 11, 12, 13, 14, and 15. And so, if I were to show this in the array, it would look like 16, 25, 17, 40, 78, 90, 18, 50, 42, and 80. And I'm leaving all these blank. Technically, they can be whatever value. I don't really care right now. If this were a 1-indexed array, just shift every... Oh, I just erased there a bit. Just shift everything over by 1. Or if this were a 0-indexed array, I would say. So this would be 16, 25, 17, 40, 78, 90, 18, 50, 42, and 80. So now, first looking at if this were one indexed. Does anyone notice a relationship between each parent and its left child? Pick a value. 3, the left child is 6. 5, the left child is 10. 4, the left child is 8. Hang on. Lag anyone? I didn't drop any frames just now. Right. When we're talking one indexed, and I have to differentiate this because the rules are not the same for 0. To go from x to the left child, the index is just 2 times x. Given that, what is the right child? If this is the left child, what is the right child? It's 2x plus 1, right? 2x plus 1. And then from there, how do I go from the child to the parent? And keep in mind, we can take advantage of integer division. X's parent. What is x's parent? We can take advantage of integer division here. X's parent is just x divided by 2. And you may think, well, wait, but what if the number's odd? Well, 5 divided by 2 is 2, remember? Because we don't use the remainder. 5 divided by 2 is 2. And so, these relationships hold. So, you can go through the array, and if I want to find the last child, it's a lot easier. I don't have to search for the last child. It's just going to be whatever the size of my array is, plus 1 in this case. Because right now I have 9, I have 10 values. So it's actually just the size. The last value is the size. My size is 10. The value at index 10 is my last value. My root is 1. It's always 1. And for any value, I can easily find the left and the right child just with these mathematical operations. Similarly, if my array were 1 indexed, or 0 indexed, I should say, if my array were 0 indexed, there's still a computation, but it's a bit trickier because the 0 indexes start from 0 and then 1, 2, 3, 4, 5, 6, 7, 8, 9. At that point, what you have to do is the parent, so x's parent, is x minus 1 divided by 2. And the right child, x's right or left child, let me start with left. X's left child is 2x plus 1. And then x's right is 2x plus 2. So these formulas are slightly trickier to remember. So that's why we often just do 1 indexed. But these formulas still hold for any value. 4 times 2 is 8, plus 1 is 9. 9 is the left child of 4. If it's 0 indexed. So you can do either 1 indexed or 0 indexed here. If we ask you some exam question about heaps that involves actually doing something with this underlying array, we will be clear to note 1 indexed or 0 indexed. If we fail to do so, you may assume either. The point is there's 2 ways to do it. And this is now we do all the same operations. So let's say I removed from this array. I'll work with the 0 indexed array. So I'm going to store the value at 1 because 1 is the root. Actually, I'm going to work with the 1 indexed array. I keep messing this up. Sorry. I'm going to store my return value. Let me do purple for this. If I were to do a remove function, I'm going to store the return value 16. That's the value at index 1, which is my root. I'm then going to copy the value at size into 16, 80, and then I'm going to just say size minus 1 immediately. So now, when I insert, I'll overwrite that 80. I don't delete it, because like this is the same we did with Q's. We can't delete this value, because what does it mean to delete it? You know, there has to be a number there. It's a spot in an array. We just don't care. We're never going to use it again. So it might as well not be there. So at this point, graphically what I have done is I have removed this node and I have replaced this value with 80. At that point, I look at my left child. I'm at index 1, so left child is times 2 is 2. It's greater, or it's less than the root, so 80 is greater than that. 80 is also greater than the right child, 2x plus 1. So I swap 80 with the smaller value, which is 17. Graphically, we would think of this as the same as doing this. But how it's actually implemented at the array level is down here. Then from there, we compare 80 to its left and its right again. The left is 90. The right is 18. 80 is greater than 90, but it is less than, or excuse me, 80 is less than 90, but 80 is greater than 18. Forgive me, I'm misspeaking a lot today, and I apologize for that. So I swap 80 and 18. I swap 3 with its right child, which graphically we would represent that as this. And now I check, and the left child, 14, and the right child, 15, are not less than size, or not less than or equal to size, so I don't bother with any more swapping. So this is where we do the operation, but we would draw it like this. And that's an important skill set to understand. One of the things that you often do in computer science is that you will make a mental model of how a problem is being solved, but you will draw it differently than that mental model is implemented. And that's because implementing something, sometimes you want to add in efficiencies. Namely, accessing this array is actually faster than accessing linked nodes by quite a bit. So we represent it this way at the program level, but we think of it in this way, and that's fine. There's nothing wrong with that. So are there any questions about heaps? Any questions at all? You go to slides. Again, this is all we did here, and again, the slides show 0 indexing. I just prefer 1 indexing because I think it's easier. When we talked about things stored in the stack versus the heap, was the same heap concept. It's worth explaining. It's worth explaining the difference. Yes, the heap is implemented like a heap, but that's abstracted from you. You don't actually have to worry about how that works. You don't have to worry about how that works. However, yes, it is implemented with a heap. I would mentally separate the idea of stack and heap as how your memory works. I would compartmentalize that as separate from the data structure heap. I'm not going to ask you how the memory works in detail on the exam because we only go over it at a high level. Will we write code for this in 2150? Maybe. I say that completely unsarcastically, not trying to be coy. I have not taught 2150, and I do know that it is taught somewhat differently between different faculty, and so I don't want to I don't want to stick my nose in and say this is what will happen because I'm not sure. Again, this is 0 index. So from there, now your daily activity, I will, real quick, you don't have to work with this. Everyone must submit individually. I encourage you to work in pairs and hop in Discord. Your daily activity today, you're just going to, you're not doing traversals. That's incorrect. You're going to, well, you are doing an in-order traversal. You're going to print an in-order traversal after 2 remove operations. So you're going to start with this heap. You're going to do 2 remove operations. You don't need to show the 2 remove. Just write what would the in-order traversal be after 2 remove operations. It won't be sorted because this isn't a binary search tree, so don't think the in-order traversal is just sorted. It's not. Then you're going to perform 3 add operations and 2 in-order traversals. So ultimately, your solution that you submit is, and I'm making these numbers up, this is not the correct answer, is going to look something like 8, 11, 9, 17, 15, 16, something like that. And then the second line is going to be something like, and again, I'm making these up. These are not the correct answers. I'm basically positive of that fact. 6, 17, 15, 16. It'll look something like that. That's what you're... wait, I'm missing a 9. A 9 will be in there somewhere. This is not the correct answer, but this is how you will submit your solution, and it's just the in-order traversals of those heaps. So that's your daily activity. With that, it's only 2:45, so I'm happy to answer questions, but otherwise I will wrap the lecture up. Are there no more readings? Yeah, correct. Well, there will be readings for exceptions and abstraction, and I'll post those just on Piazza. Yeah, like everything I've talked about in trees is covered 17.1 to 17.4. 17.5, if I recall, gets into red-black trees. You're welcome to read that, but it's certainly not required for this class. Personally, I've always preferred AVL trees myself. Technically, red-black's more efficient. But AVL's easier to explain in my mind. Alright, with no other questions then, I will end the stream. Thank you all for watching. I'm sure I'll see some of you in office hours, and I will see the rest of you tomorrow. Take care.